Okay, so let's start. Okay, thank you.
So let me first thank organizers for chance to this. So a little bit forward, this is the work that I actually did 7 years ago when I was a student. I'm sorry, a postdoc in Stony Brook. And we didn't really put this paper out until last year. And I now thank God for this delay, because now I can present it as a recent work rather than a work 7 years old. So it's nice to have something to tell.
It's a vintage work, huh?
Yes,
it's aged well.
Well, but we kept it secret. It's not that cool. So let me just remind you this well-known fact that high energy or low T, T is the T channel change momentum scattering is non-perturbative because it's large-scale physics, long distance, transverse distance, and in that regime, it's natural to think of this problem in a light degrees of freedom in confinement regime, which is QCD string flux tube. And I view this really as a tunneling problem because just looking at the problem in this way, this string tension gives a potential as a distance from the source of the string. So there's a linear potential, string tension. But when this other end point of string find the this fast-moving projectile, then as soon as it finds that point, it is accelerated and it gets huge energy, and then it can hadronize. Essentially, the string can free from confinement. So just pictorially, this is really a quantum tunneling problem crossing this linear potential barrier. But on the other hand, this is not as simple as that just quantum mechanical problem, because the degrees of freedom is really extended string, first of all. And also, this is really a time-dependent problem, because the other string is moving fast. So the string endpoint has to be right on time, catch that other projectile to be able to actually tunnel through this potential barrier. So this is really a time-dependent quantum tunneling problem, I think, and this is why this problem is very difficult to solve. It's not perturbative, but this way of thinking naturally leads us to look at some possible Euclidean instantons responding to this tunneling problem. So that kind of motivates this word string instantons. So our object is not just particle, but really string object. But maybe we can look at some classical solutions of these strings actions in Euclidean space with boundary conditions set by this two moving projectile with large reflected gap. Then these instantons might really capture this non-perturbative tunneling dynamics as in the case of the usual quantum tunneling problem. And also there's another aspect. If we look at this expression, which essentially gives you the Reggeon trajectory. So B is the impact parameter distance. This is a, I think that doesn't work, but
what doesn't work?
Maybe I should just stick. Yeah, the stick is fine.
The old-fashioned way. Very good.
But
you have to be able to change your slide.
Yes, I should keep that. Yeah.
You have to
okay,
keep that
so
change your.
no, give me. Oh, no, keep it.
Right. Right.
Okay, so this is a impact parameter representation of the say Pomeron or Reggeon amplitude, where D is the impact parameter distance and chi is the reflected gap. And if you compare this expression to the usual Schwinger tunneling formula, where m is the mass of the charged particle and E is the electric field, you see a lot of similarity between the two, where B is proportional to the mass of your string, right? The string mass is proportional to the length scale. And then it can also be shown in our work. This work was really in 2012, which was 6 or 7 years ago, that we actually showed explicitly that in fact, by doing some duality on this two-dimensional string worksheet, you can actually translate this rapidity gap between the projectile into actually effective electric field. So we could also understand this string instantons as kind of effective Schrödinger mechanism going on there. So, all right. So what we are looking for is some Euclidean semi-classical two-dimensional worksheet. Imagine that you have one-dimensional string in real space, and if we consider also the time Euclidean space, what string corresponds to is really two-dimensional surface. So let's look at Euclidean semi-classical two-dimensional worksheets. They are bounded by this two projectiles, and also record that this endpoint of string usually represent the color charge parity networks and antiquarks and so on. And for charged neutron pomerons, simply means that there's no charge exchange between the two. Then it is easy to see that this string should be closed string. On the other hand, for the regions that I'm focusing in this work, where the exchanged object is actually a antiquark pair with a quantum number of mesons, then we should think of open strings instead of twisting strings. Okay, so this string instantons in Euclidean space are known already for pomerons and regions. So these are some of the old references. And also,
So I'm sorry,
Yeah.
probably just needs to know this logistics.
Yeah.
Why do you call it instantons? Is it just usual?
oh, because so just give you just one slide picture. So I like to consider this long distance scattering problem as the quantum tunnel problem of strings from one projectile to the other, because the string energy is proportional to the length distance. So there's linear potential.
Linear potential
Oh.
between
Linear potential as a function of the distance string travels. Because
so
string
for this
endpoint
quark
travels.
and antiquark. So scattering quark and antiquark.
It could be anything. So suppose the string, suppose you have two hadrons that meet each other, and the impact parameter is large. It has to go through this confining vacuum between the two, and the right degrees of freedom should be some string object.
In QCD?
In QCD, yes. In QCD,
So
not ADS yet. Well, I mentioned about some connections in ADS, but this is just a QCD string, right? So, and then
So the QCD is attached to one of the projects, and
Yes.
the other endpoint is
right, yes. So this could be like virtual strings that tries to probe
so
some.
the tunneling is
some
the
large
tunneling of the
distance.
endpoint or
Yes, precisely. I'm sorry. So this is distance of the string endpoint. The other endpoint.
So the endpoint actually is tunneling, right?
Yes, precisely. And there is a potential barrier as a function of distance x here because of string tension. So there's a linear potential gap. So that prohibits this mechanism in large distance. But as soon as it gets to the other projectile, which carries a lot of energy, as soon as it gets to the point, it gains a lot of energy and it can hadronize. So that's the point where effective potential just drops. So
No, so it just goes flat.
right. Well, it could flat, but it can get more energy, right? We can accelerate it. So this is just a schematic picture. This is not really a static potential problem. This is really time-dependent tunneling problem. The string endpoint has to meet this other point exactly at the time when it passes through. So, but we can include those. We can include those features in the Euclidean geometry, just by considering, say, this picture. So this is an Euclideanized picture of two objects moving with some relative rapidity, and then we can consider some of this Euclidean two-dimensional string version as
So this is
tunneling.
again QCD string.
Yes,
So
this is
like
QCD. Yeah, yes,
string.
yes. I'm not yet invoking any of this.
So this is like global exchanges, really?
Yeah.
But the blue balls would be on the Pomeroy trajectory, right? On
Right.
string trajectory.
Yes. So this motivates really to look for some classical solutions of string actions with right boundary condition of this colliding geometry. And so now I mentioned a little bit about this, what has been known and what we are going to do. So what I'm going to explain is, but also in decoupling particular QCD, we have we know the TQCD description is in terms of this lateral gluons, BFKL. But since this is really a tunneling problem, I just wonder whether we can ask similar question in Euclidean space by solving some classical mills with the right boundary conditions. So these two colored objects. So I pose this as I don't know. So now ADS safety. Okay. So by the way, this non-perturbative strong coupling nature naturally led people to think of this problem in the frame of ADS safety, and there have been a lot of work and with a lot of intuition also. And it can be shown that in this large distance regime, the strings kind of stay in the more and more IR regime. It's natural because large distance is more IR. And if there is really a lambda QCD, which is the bottom of this space-time, then this bulk of the string will just stay at the bottom here without further moving into the I region. In that case, the dominant dynamics is precisely similar to just the split plus one dimensional dynamics. So it essentially goes back to the original QCD string picture, where the additional this ADS-CFT dimension doesn't play much role in that regime. So I think in this particular regime of really low T physics, I guess essentially we have just we essentially go back to the usual QCD picture.
You're saying you have some infrared cutoff and you still
Yes, string will just
drag
stay
along
there.
the cutoff,
Sure.
and then the little segments when they go out to the
Right,
roundabout, or they're pretty much the same all the time.
Yes, yeah. So in that particular regime, what has been kind of it is natural to actually reproduce this picture. But there are a lot of interesting things like the DIS picture, and that involves the really additional dimensions. But for this like total cross-section problem, I don't think that there is much this
Total
additional
cross-section for what?
or this large energy scatter, which is governed by low T.
But Corponium and Corponium.
It could be any hadron. It could be corponium. Any hadrons which can emit strings. But anyway, let's go on here. So now this rapidity gap is really a Minkowski concept, but we can easily translate that to the angle in the longitudinal space, time and directional motion, this two-dimensional space, by this analytic continuation. This was observed. This was pointed out here. And it is easy to understand just by looking at the metric. So this is a usual Euclidean metric in boost coordinate, and then chi is the rapidity. Now tau becomes IR, and then chi becomes minus I. pi zeta, and then you see that this rapidity gap indeed becomes just the angle between two word lines of the projectiles, where B is the transverse separation.
But in ADS, you can just work in Lorentz. Why do you need to do this?
Because we are looking for instantons. As a because this is commonly problem. I'd like to find some semi-classical instantons representing this commonly problem.
I guess it might be a Spaleron if you went to
Yes, it's Spaleron and instanton.
if you went to Minkowski space, yeah.
But these two objects have very different physics.
Yeah.
So, yes. So I think this should be instanton rather than.
And a small comment which I already made a few days ago, it's not the rapidity gap, it's the rapidity interval.
Rapidity interval,
Talking
I'm sorry.
about different-
Okay. Okay, thanks. Yeah. So I'll check this rapidity interval. So after finding this, say, instantons, suppose we found one as a function of d. Pi here, it's an angle. And then Euclidean action or Euclidean amplitude, which is just given by that. And then we can easily go to the T space, momentum space, by this Eichhorn expression here. And then by optical theorem, total cross-section is simply given by the integral of the impact parameter space over this essentially this instant action. So now the quest is to find really this classical solution, and now QED is usually neglected in those considerations because essentially because we assume the QED interaction is weak. It doesn't really affect the kind of major QCD effect represented by the string worksheet. And what QED does is simply multiply this Wilson line factor in the total string amplitude, total scattering amplitude, and when we go to the T space, we could easily have some interference effect between this string worksheet physics of QCD and the QED, and this seems okay for the projectile whose charges are small, PT or VP. But our a simple motivation for this work was that in TA collisions where one of the charge is like factor 100, so order of 100, then clearly QED is not weak; it's actually strong QED. So then this Wilson line contribution may be comparable to actually QCD contribution represented by the string action. And what we have to consider in the saddle point of analysis is not just the QCD action of the string, but the sum of the QCD and QED. And I will show you that indeed the classical solution of this combined action, this limit, is significantly different from what you get without QED interaction. That means the QED can really affect the QCD dynamics itself at the leading level. It's not just the interference. QED actually changes the QCD physics strongly.
But QED problem itself can be, of course, solved without ADS. Just include multiple photon exchanges. I think Kirill
first of all, this is not.
some years
Okay. You mean this PQCD?
ago.
PQED.
PQED. Okay. I see. With some gluon matters.
No, not gluons. Just photons.
Photon exchange.
Okay.
Yes.
Not multi-photon.
That should be just Wilson line. QED is a linear series.
It's a little
In
less-
Eichhorn limit, it's just Wilson line, right?
It's a little more subtle. Maybe it is a line, but it's different from QCD.
I think in maybe a little bit different in our setup because by Wilson line I mean the Wilson line along this exchange program.
No, I understand what you're saying. I'm trying to remember there were some issues there which are probably not very relevant, but you know, like two-ion exchange could be, for instance, in the singlet mounted, and one is is purely so singlet is purely imaginary. Also, this
isn't that
the photons things somehow counting is different. So, in other words, for instance, the lowest order interaction with muons, you have to exchange two things, because you have to have the total cross section. You have to have color singlet interactions. Right? But for photons, you can just exchange one photon. So there are issues there.
Right,
so you're probably right to just say, oh, it's just Wilson lines. But then when you start evaluating those Wilson lines to calculate the cross sections, it seems
If it's a charged hadron, if you were doing neutral hadrons like Williams, I think you would have to have two photons also.
yeah, like neutron scattering.
Or Oleum.
Or
Just have
just-
J-side scattering.
Yeah, charge zero. But I thought you had PA somewhere, right?
Yeah, this, so imagine this is A and this is P.
Okay.
Then this is A has
Right, it's big charge. Right.
produces
Right.
So this is-
Kirill Tuchin worked it out like 3 or 4 years ago for DIS. All those multi-photon exchanges. So it's kind of
But
interesting.
isn't it actually kind of small because I mean, I don't know, I'm just guessing. I would have thought the real parameter is alpha over pi, and that the z is less than 100, and alpha over pi is 1 over 500, and that you still have a small parameter.
I don't know if physically the QED scattering dominates the elastic cross section at t equals 0.
Oh, of course, but that's the photon pole, right?
Yeah.
But that's right. If you go out to transverse momenta on the order of 100 and 200 MeV, then you get rid of all that.
I remember he was finding like 15 to 20% effects.
Okay, great.
So it's
Well,
not-
one over, absolutely, absolutely.
You have the QED contribution which
Just
is falling very
15%,
fast,
I
and
agree.
the QED contribution which is not falling as fast. Like T is like there's some coverage range where they're compatible.
15-20% even at moderate T values. But you're of course right. If you go to zero momentum transfer, you get this gigantic Kuhn peak.
yes. So
Okay.
yes, QED interaction itself might be strong too. What we have looked at is actually this effect of QED on these open strings, which are charged on the boundary here. So how this strong field produced by, say, nucleus affects this string exchange dynamics. So that's the problem we are looking at here. So let me just give you a short summary of what was known before about this string instance in the case without any QED. So in Euclidean space, because of positive invariant, we can always go to the rest frame of one projectile. So the one projectile is here, straight line along Euclidean time direction, and the other projectile, which is separated by distance d along x1 direction, is tilted by angle theta. Remember, theta represents rapidity gap in space. And then, the string should join these two lines, twisted by angle theta along the distance b. And with a little bit of thinking, as was correctly guessed by Yannick Chansky, that it to a very good approximation that the string worship, which minimizes the total area. By the way, I should mention that this action of the string in Euclidean space is simply the area of string worship, because area represents string distance, which is proportional string distance, which gives you the energy, essentially the energy of the string times the time propagation t. So string action is actually just area in the space. So we like to minimize the string action with this boundary condition set by these two projectiles with theta. And it's natural, and it's very easy to realize that minimum configuration obtained when the string worship lies in some a surface called helicoid. So helicoid is obtained so helicoid consists of twisted lines in angles as we travel distance b, linearly as a distance, such a way that when it gets to the distance b, it has angle theta. So you should think of this kind of continuously rotating lines along the direction b, and the surface obtained by those lines is called helicoid, and our string worship has to sit on that surface. And the useful parameterization of that helicoid is in terms of two parameters, sigma and tau. Sigma essentially represents the transport distance. Tau represents the length, essentially the length of the segment of the string worship when you cut this string worship by a constant sigma surface. So think of tau represent the distance between these 2 points at a fixed sigma. Okay, and the tau is, so zeta sigma is this twisted angle depending on sigma, linearly dependent on sigma here, and then tau is this coefficient of cosine and sine. So this is really just this. So you see that in this way, the only parameter that that determines the surface is actually this function tau sigma. Okay. So tau sets the range of the string worship in the tau direction at a given point in sigma. So sigma runs in this direction, and at one point in sigma, tau represents a range in the orthogonal direction.
I'm not sure I understand so I thought I understood the red arrows, but here, I mean, we're only in time, right? So the x naught axis, right? So you're both in time. So what's the meaning then of the arrow there?
Here.
The red arrow line.
Red one.
Yeah,
Right. So red curves represent the boundaries of our string worship. So the string worship is two-dimensional surface bounded by first these two projectiles.
so same
and
I look at the fixed
curve.
fixed x naught.
Fixed x naught. Fixed x naught will be a complicated surface. So because your surface is twisted in x0, x3 surface, where x3 is the direction of propagation in Euclidean space. Right? So if you cut it in constant x0, it will be some other curve, but that's not a useful way of looking at the surface. The most convenient way is to parameterize this as a function of parameterize it in terms of distance in transverse space, and a range in the helicoid orthogonal to that direction spanned by the surface. Yeah, yes. I'm sorry. This picture might be confusing. Yeah.
So there's another axis, right? The third axis, and it's string.
Yeah, you can see it on the
So
right.
these are 2 points of the string, right?
See the x3 is pointing in there over in the picture. See the x3 and the
Yes,
x1?
yes. So
Yeah.
when I cross the
Right.
I take
Yeah,
the
X3,
constant x naught, I'm picking the endpoints, 2 points that are crossing the 2 points of the string that are crossing the
Yes. So this
plane
red line
is not
represents the string trajectory in
Okay.
Euclidean space. Decided the endpoint of the.
Right.
Yes.
So I'm not sure I understand.
Yes, I'm sorry.
So the
Yeah,
string
I
stretches.
try my best to
Sorry, so
visualize
let me
it.
just ask a question.
Yeah.
So the string stretches between the two quarks.
It's not just one dimensional. We should think of two
No,
dimensional.
I understand, of course, that there is kind of an angle, but isn't the string worship just a set of straight lines connecting them? Or no?
No,
Maybe.
Okay, why
no. Because the string can go out of the, the string can wobble in the spatial direction.
Right, but why does it have those red boundaries?
Because we are
boundary
considering
of the
open
string.
strings. Yeah.
The
We are
boundary
considering
of the
open
string.
regions which have.
Those are the quarks. So at the end point of the string is, no, I'm not saying.
No. That's right.
That's right.
The point of
That's
string.
That's the quark.
so
yeah.
that
Quark, anti-quark.
What are the blue lines?
Blue lines are the word line trajectory of the two projectiles in Euclidean space.
Which have two quarks.
Which hadrons or like
Okay,
nucleus,
yeah.
some large nucleus in the PA case. So one is P and the other is A, and they exchange It's called article pair.
Could you draw a 3D picture? of
Yes.
the board?
uh,
Well, I will request the INT to install a 3D player.
So,
For the video stuff.
so this is a one word line of one projectile moving straight in say Euclidean time direction. It could be also have
Moving.
So it's rest. It's at rest.
It's addressed.
It's at rest, but
Yes.
but it doesn't matter because there's a rotational symmetry here. That's just Bruce's symmetry. But only what matters is just angle between the two.
Yeah, that's fine.
Yes.
So
So we can always
You
just
Yeah.
boost into the west frame of
Yes,
the
precisely.
target,
Yes,
so to
yes, right. Precisely. And then there's a distance here, which is impact parameter here, and then and think of longitudinal direction of pointing into the blackboard, and then so there's another word line of other trajectory. So I would draw it like this.
is it the
But-
next not X1?
But it's not tilting this way, but it's tilting the other way now. And then string worship has to be something like this, joining the two.
So why is there like upper boundary involved?
Because I'm considering regions, not homonorms. So I'm considering Q-bar exchange rather than closed string homonorm exchange. Probably you have this.
No, I heard you say that, but I didn't connect to this
Yeah.
picture somehow.
So right. And they are charged under electromagnetism because quarks are charged in general.
So for that, one of your projectiles should be a quark, the other one is an anti-quark?
No. The projectile can be, say, P and A. They source string worship.
So the proton,
They-
right, the proton has 3 quarks. One of them goes over,
Yeah,
and leaves a string connecting it.
but it has to become,
Yes,
to connect to an anti-quark.
Yes,
somewhere.
yes. Precisely. That,
That's what I mean.
Yeah.
So, okay,
And-
some C anti-quark.
yes. And indeed that brings additional factor 1 over S by overlap of Dirac spinors moving in opposite direction.
So this Q bar it's a color object.
Q bar, it could be,
So it's
no,
kind of a
here I
Reggeon,
think
right?
it's
No, it could be a single.
singlet, yes.
But if it says it's a Reggeon,
Reggeon is
That
not
makes me-
Reggeon, it's a pure one.
So he wants
Reggeon
Reggeon,
is a
right?
Q-bar and a single.
This is like measured exchange.
It's like a BFK leather with quarks in the kitchen, but overall in the single state.
okay.
It's not a Reggeon.
Okay, so now I parameterize this x1 with sigma here. So sigma runs from 0 to b, and each sigma, the helicoid surface has a intersection of the surface with a constant sigma plane gives you a line here,
But it's really a
which is
sheet,
also
right?
tilted by some angle, but that
It's a
angle
whole sheet. It goes between the
flows linearly from 0
and
to
between the
Z.
quarks.
That's a straight line.
That's a straight line. Yes, that's a straight line, and this straight line is parameterized by
Angle
x0
changes in the
tau sigma cosine zeta sigma, where zeta sigma is a linear function which grows from 0 to zeta.
This is already just
Yeah.
after you did the math and minimize the action, right? Found the classic.
Right. And then
Yes, this is a guess. So
Oh, it's like you always like the same
Yeah,
card.
the string only exists for a certain time.
that was
And
done
very,
by
very few times.
so they propose that natural
At some point,
restricts the surface at the beginning because that
when the network starts to move pieces
space
together,
that should minimize the
and
action.
then at the
So-
later times there's a sheet, then at later times the string is
so this-
gone and you're
There's
back to
one
after the
curve,
scattering, there's no
how
connection
sigma
between
that
the two.
determines
The lifetime of the string.
string. Yeah. So this tau sigma represent this line here. So essentially tau sigma is the length of the
So
string.
is this a line in X0, X3?
X not X3 space, which is the
But
space.
that is not a straight line. Just,
That's the straight line, right?
X0
It
is
has
not
direction
proportional.
given by zeta sigma, the constant sigma. We just change tau.
Wait, tau is a function or?
Yeah. Tau is a parameter. So tau represents.
Okay, tau is a
Yeah. This is a
okay.
parameter for the line,
Yes,
straight
yes,
line.
Yes, okay.
And then it's the location of the boundary. You can parameter by this function tau sigma. So so tau runs from tau sigma.
So when you put tau sigma, those are the endpoints.
Those are the endpoints.
Plus or minus.
Yes, right. So the string worksheet is spanned by this range, by this domain in tau sigma space. So, yes, I know this is my picture is not really clear enough. I mean, it's a little bit hard because you have to draw 4 dimension and a 3 dimension.
So I think this extra line in the middle will improve the picture.
Here, yes.
Yeah, that was a plain cross section.
Yeah, I completely. I thought about it, but I didn't have time to.
So you have to make it so it wouldn't be too congested.
Yeah. All right. So with that, then the analysis is quite simple. So you just compute action, which is nothing but area here. Now, because theta is I times rapidity interval here, you actually have this, and your tau sigma is the variational parameter to minimize this action. And you see that under the variation of type sigma, what you get is just this value at the tau sigma, and we want this to be 0. So this classical equation of motion is simply this algebraic equation, which tells you that tau sigma, which is the range here, is independent on sigma. So it's just a square shape, whose value, whose size is given by b over chi. So it's proportional to b, and also inversely proportional to the. And with this classical solution, it's easy to compute instant action. That gives precisely the action you need to produce Reggeon QED. So this correctly produces Reggeon. And it is also possible to obtain the intercept, which is the value at t equals 0, that essentially determines the total cross-section by optical theorem. And this S1 loop can be computed from considering the one loop fluctuations of this string worksheet here. And then since this string worksheet is highly elongated in large high limit, what you get from this one loop fluctuation is nothing but just Casimir energy. This is a time and this is an interval Casimir energy. And Casimir energy is well known to be pi over 24 times ratio here. And you indeed get something that precisely gives you intercept. So numerically, experimentally intercept 0.3 or something.
You mean the slope?
No, this is not slope.
I
It's
have.
intercept.
The traditional numbers I have, right?
Yeah.
Oh, it's a half? Okay, yeah, so it's still kind of smaller.
Oh, that's why it got thrown off, because the slope is point.
Slope is
No, this is the Reggeon, not the
Not for the
Palmer.
Reggeon.
This is the Reggeon, not the Palmer.
okay. So now,
So why did, I'm sorry, I'm returning to my own question. Why is it an instant one? Is that topology?
no. This is just a
Because
classical
it's a
solution of equation motion in Euclidean space. They represent tunneling between two projectiles. So it's
Well, it's your
called-
interpretation of it as tunneling, right? Otherwise, the principle, like take any string solution in ADS, right? It's classical like a code.
By the way, this is not just in ADS. This is quite generic. I'm considering it as well.
So usually
But-
tunneling, you have someplace you have a very small probability, right? Because tunnelings usually have,
Yes.
where's your small parameter?
Here we have action growing spherically with distance b. And
So if we took B to be 1 Fermi, which is a typical scattering,
Right.
we took alpha prime to be 1, but in GeV units, do you really have a small parameter in sort of a high energy scattering context of realistic parameters of 1 Fermi and the slope parameter, etc.
I think you want B to be larger than 1 Fermi.
But you don't want B to be larger than 1 Fermi to do most of the cross section.
Right, right. This is not really trying to explain what you mean, but I guess by optical theorem, please correct me if I'm wrong. By optical theorem, this dominance.
There's no optical theorem. We're doing Reggeon exchange, so we're not going to.
Yes.
I think the problem chi is sort of like rapidity, right?
Chi is the rapidity.
So if it's really high energy scattering, then it's actually a very small parameter.
You said that the large rapidity will make this.
No, it's something that.
It's the other way around. Because
if
the instanton action should be gigantic,
right, that's what
and
I'm saying.
the rapidity is going to make it very small.
Yes. So it becomes gigantic because B in T goes to 0 limit becomes larger and larger. It's larger and larger.
No, it doesn't. No, it doesn't.
Zero limit is integral over B.
But the B is never larger than.
Oh
the
yes,
Fermi.
yeah, you're right.
In real
yes,
physics,
yes,
in real physics,
that's right. Yes,
B
sure,
is
yeah.
never larger than
It's
Fermi.
integral, but yes, you're right. So dominant B is actually square root of chi. Yes, you're correct. So if chi is large, then this integral dominates by large.
B never gets large. Oh, well, yeah, you're right. No, B does get large like the square root of.
Yes, also the S instanton gets B gets so large that the S instanton is on order 1. That's the largest value.
Yeah. Right. Yeah. Because the important region is where this factor is
So it's
over
chi
1.
prime is the real parameter. If chi prime were very small, then the instanton picture would be very good, right? It's the chi prime.
Alpha prime.
I'm sorry, alpha prime. Excuse me. I said wrong. It's the alpha prime which is really the parameter.
Oh.
If alpha prime goes small, you have a genuine instanton.
So now we can now move on to regions with PA, where one projectile is heavily charged. Then this, in addition to this area of the string, which constitute the QCD contribution to the action, these lines which are charged by Cork antiquarks get a huge Wilson line from the gauge field, QED gauge field produced by the Z. And its Euclidean geometry, it is trivial to solve this QED equation motion with sources of Z here. That's just a Coulomb potential. It's very easy. And then we can now compute the Wilson line here, depending on this trajectory function, tau sigma. Still assuming that this worksheet still lives on helical. That's our assumption we took. So now we can compute this QED action. And in normal situation where QED effect is not interplaying with the QCD, then we can easily check that this QED action becomes purely imaginary if you go to the Minkowski space by analytic transformation. So now we will show that as a result of interplay, then this QED action really gets a real form too. So that's the kind of.
I'm sorry, are we in the ABS space?
No, not. So I already discussed connection to ABS. So since we are looking at large T, small T regime, most of string are sitting at the bottom of the wall.
I see.
So essentially this goes back to the QCD string picture, but we can easily embed this to ABS too, if you want. Okay. So this is the expression for the Wilson line here. Essentially, this is just the integral of A0 here along this curve shape.
So your model would never give us Bjorken scaling.
Let me see. So
because it's kind of like the old string models, right?
Yeah.
And that's why they kind of died.
Yeah. Okay. So let's get to the end point. Then we can discuss about the
Then you can complain.
Right. Yeah. So
Okay.
right. So this is the expression, and then we can easily find the equation of motion with combined action. So this is what we had before, QCD worship area. and this is really QED, the streamline part, and we now solve this coupled equation, assuming that z is sufficiently large that this is actually not small, not that small compared to the first.
So you use the solution that you get from the action in the QCD case.
Yes, so in the
You
QCD,
minimize everything at the same time.
right, so now I like to do set point with this combined action, including QED, not just the
Right. What is Q?
QU is the charge of the up quark. I'm assuming that this line is up quark, down quark, but it doesn't need to be that. So QU is the charge of electromagnetic charge of the quark line here. Okay. So then we see some interesting features in the solution. So we find two branches of solutions. So this is a sigma here, and y sigma is the square root of tau here. No, I'm sorry, square of the tau. And this upper branch can be shown to be perturbative in parameter here. And it ceases to exist beyond some critical distance sigma here. So it just blows up and then it doesn't exist here.
So when you go into these small, say 2 Fermi, is your nucleus a point-like nucleus, or you actually have the charge spreading out? Because the nucleus is 7 Fermis.
Oh yes, that's right. I think that's a good question. I think our B here is probably much larger than.
Yeah, but is the nucleus? Is the nucleus?
It may be related to this parameter R0 that so R0 is really a kind of distance within the projectile.
Okay.
Between the quark. It's like a spreading of the quark inside the projectile.
Right.
So we put it as a regulator.
Right. So in a nucleus that might be 6, 7 Fermis, I guess.
For nucleus, yes, I think so.
Yeah. Okay.
But for our numerical analysis, we just took 1%.
Well, you see, that's the question. The question is,
Yes.
you're finding this kind of singularity, so
Yes.
to speak,
Yes.
around 2 Fermis.
So
So I'm
yes.
asking the question:
I see.
is that for a point-like nucleus, or is it for a nucleus which
I
is
think,
spread out over
you're right.
7 Fermis?
You're right.
I was thinking 2 Fermis is just he has 2 1 Fermi nuclei scattering, and 1 plus 1 is.
Yeah, I know, but the nucleus size is 7 Fermis. What is
No,
that?
I'm not saying it's realistic.
No, but that was just the question I was asking him, whether his nucleus is point-like or not.
Right. But the related question is what happens if he has a 6 Fermi nucleus? The distance would the distance be 1 plus 6 and 7?
So the question is how does sigma c depend on
Yes.
R0?
Yes. So indeed, well, R0 is
1 Fermi there. Yes.
yes, it's R0. But now let's see. So this is kind of rough behavior of sigma c as a function of impact parameter b and chi. And recalling that p square should be order of chi. This means that sigma c goes to small when chi is large, and then it may be inside. So that's an issue. Yes,
That's
so,
an issue,
yeah,
right?
yes,
Right. It's a question. It's an interesting calculation in any case. But it's a question of if you took a big nucleus and you spread it out, you might not be so sensitive to all of the charge when you take these parameters small.
Yeah.
We only may see the parts of the charge may be suppressed by distance factors.
Then maybe effective z might be reduced.
Maybe effective Z might be
Yes,
reduced.
so
Exactly.
there's an issue.
The effects may not be a problem.
Right. Okay. Okay. So with that caveat, so the other branch of solution is really non-perturbative, and it just becomes exponentially small beyond that same sigma c, and it stays almost constant here below that sigma here, below sigma c, and that value, that constant value, is determined by this algebraic equation. So first of all, when this z is so large that actually if this becomes negative, that simply means that tau becomes imaginary solution, and our whole action becomes purely imaginary. And we can look at this as a kind of realization of complete QED dominance over QCD. Everything becomes just imaginary, pure phase. QCD physics just disappears, and then, but with our reasonable parameters, we can see that this never happens. So that's just a comment. And so with this solution, we can easily now find the real part of the. So there's some imaginary part produced by QED action, and then, but this real part is simply given by the area of the string worksheet that I presented in the figure, and this is the.
But because the electric field becomes so strong that you produce charge antiparticle charges, or what?
You mean this?
Where do you get this imaginary part? Yeah.
Oh, you mean this one? QED don't. So.
I mean, why can I not take Z to infinity? If something happens there, do you, like the string snaps somehow, you screen the charges or what?
Yes, yes. Indeed, this tau becomes, so tau goes to 0, and then it becomes an imaginary solution. So your action becomes imaginary. And I don't have good interpretation, but indeed, the string really disappears in some sense. Okay.
But the string disappearing, I mean, you're exchanging flavor. And so, how does a
this solution becomes just saddle point in complex space, I would say, and its value is just imaginary.
I mean, this is what we saw for various string configurations. I mean, that's what happens, say, for the heavy core potential in ADS, right? Once you get a certain value of the separation between quark and antiquark, the real string solution doesn't exist anymore.
Yeah, but that separation is done by a singlet exchange usually.
Yeah.
This is a flavor non-singlet exchange.
You're asking what?
And it was a finite
And so it's not,
structure.
see, because it's a flavor non-singlet exchange, it's not so easy just to pull these things apart. Because the initial hadron and the final hadron have different flavors. So this is proton going to neutron scattering, say. This is proton on a nucleus going to neutron on a nucleus, a different nucleus.
So there was a paper, so we saw this complex configurations, yes, in the single case, long time ago. And since then, there has been a paper where people kind of find the same dynamics, but you know, if you look at the defined temperature heavy core potential, you're looking at static string configurations. And if the static string goes complex, the question was, what does it mean? It doesn't really mean that the string disappears. So there was a paper by a Japanese group. I can come up with names if I think a little bit. And they actually had some we looked for a dynamical solution. So the string all of a sudden will start oscillating. And that reproduced, at least at the qualitative and semi-quantitative level, a lot of things we saw with the imaginary string. So the potential got an imaginary part and all that. So
This could be like that.
yeah, maybe this could be like that. The disappearance of a real solution with these assumptions means that it's a more, maybe it's a more dynamical solution. So, and this is why you have that, like, did you show the plot where you had all those?
Yes.
Yeah. So this is why you have sort of different branches because of the complex number, or why they have different branches.
So, so this solution can be obtained. I'm sorry, I should say this way. So this solution can be continuously connected to the perturbative solution in small z region. You can show that this part, say, can be yes. But this solution, which is really disconnected solution from that perturbative branch, is a new solution appearing only in large z region. So,
but it's completely imaginary.
No. This
it's all real.
It's all real. Yeah, this is all real.
Which solution will be realized?
This bottom branch, yeah, non-perturbative branch, because the perturbative solution ceases to exist and its action is purely imaginary, so it doesn't contribute to the real part. if you compute the action with that solution, we can see that the QCD action, this total action individually all become purely imaginary when you go to the Minkowski space. So, but this solution has a real part, and then we choose this solution as a suitable instantaneous.
But then for small z, you're not going to recover.
Small z, I have a plot too. So what happens is that essentially there is a very singular behavior around this point. So at small z, they meet actually. They meet, these two branches meet here. And you can think of the whole thing as a real solution.
So there's some z critical.
I'm sorry?
There must be some z critical where you change the behavior.
Yeah, so let me see whether I really see the trench, but so something really blows up so let me first explain what I mean by alpha prime z. Alpha prime z is this coefficient here, and this alpha prime z really blows up as z gets smaller and smaller, which means that our action becomes 0. So that means that this part becomes smaller and smaller. And in that small z limit, essentially our perturbed solution dominates the solution. So this regime, this part disappears. So this part appears as z increases more and more important. So this dependence is somewhat different from the usual region. We call the usual region was b squared over chi. Now we have b squared over chi square. And in the t space, we get some strange looking expression of log as squaring the exponent. And then optical theorem total cross section is bounded like this. And it is stronger bound than Forsyth bound, of course. It cannot exceed Forsyth bound. So it's okay with the bound if someone.
But you see, that of course that's very unnatural for flavor singulation, and there is no such theorem in axiomatic field theory. You see, the log squared has a very trivial understanding in the Froissart bound case. You have a rising. This is the Heisenberg explanation ages ago. You have a rising potential with a power, and you have a Gaussian fall off, and so they meet at a radius on the order of log of s, and pi r squared then is log squared of s. Here you don't ever have that because you don't have any unitarity limit because you're 1 over s, and so somehow this is a very unnatural result here.
Worried about log squared.
Yeah. Log squared is unnatural in this context because it's got a 1 over s, and somehow the log squared was defined by things being about 1.
Right.
And nevertheless, it's curious.
Yeah, it's curious. This is what we just get from this analysis. But I like to emphasize that this happens only when z is sufficiently large, so the QED significant effect is QCD dynamics.
Right.
Otherwise, this doesn't happen.
What happens if z is small?
Z is small, then this alpha prime z blows up.
You see, that's the other thing that's a bit strange. You see, in the pure QED case, you have cross sections which don't have 1 over s's in them. So the calculation that Yuri was describing that Kirill did, I don't think that would have had a 1 over s in the cross section.
Maybe I have some explanation about this 1 over s, the origin of 1 over s.
Okay.
So our 1 over s came in the beginning from the spin factor, spin overlap.
I agree.
This is this quark, and so we have to overlap with spinner moving this way and that direction.
Okay, very good.
Yes,
very good. So the 1 over s is fundamentally the quark.
Yes,
case.
it's just quark.
Yes.
Right, but if QED dominates in that regime, the cross section would not have. Right? It's completely.
Yeah, but QED couldn't completely dominate in this process because it's flavor exchange. QED can't give you flavor exchange.
Forget.
All right, so I think that's the end of my talk. So
Yeah.
thank you. Thank you.
Question?
Any predictions for GIS?
He's
like I told you,
gonna
this
write
is
something up in the end here, right?
No. You guys are all writing.
Yeah. Okay.
I'm
Nice.
compiling.
I mean, this is all about semi-classical solutions.
I mean, it seems like not a big deal to replace your problem by a typo.
Right. But this approach, I guess, I mean, we are looking at semi-classical regime. We are not really looking at wave functions. So I think this happens only in the large distance.
So why does it not apply?
So he's saying the very small dipole that you would have in deep inelastic scattering would not couple
Yes,
nicely
so
to this
we are really not
non-perturbative
sensitive
string.
about any
Okay,
structure here.
photo production or something. Right?
Photo
A
production,
real
sure.
large dipole.
Sure. Photo
Q
production.
squared low, so not deep, shallow inelastic.
Yes.
Totally would work, right?
Yeah.
So you can make predictions for EIC.
Okay, so I should ask you more.
I'm sure I can help with all the details.
Sure, photo production of a row meson, for example, we have the flavor exchange, and then you have a Reggeon.
Oh,
Photo production of a row
Right,
meson.
right. And that's a very measurable thing.
yes, yeah. I think you can select event by quantum number of exchange.
Yeah, no.
Yes.
All right, if there's no further question. Okay, let's